Newton's second law of rotation for an accelerating frame. When the axis of rotation is fixed, we have discussed how to solve the problems of rotation. When the axis of rotation, suppose the pivot, this is the axis of rotation, this moves or accelerates. Let us assume that this point P or the pivot or the axis of rotation moves with the velocity Vp, and the center of mass moves with the velocity Vc, and the rigid body rotates with an angular velocity omega. In this case, let us calculate the angular momentum of the rigid body about this point. The angular momentum of the rigid body about the point P is given as L is equal to angular momentum of the rigid body about the center of mass axis, that is LC, plus angular momentum of the rigid body's center of mass with respect to the given axis or given point. This is the axis. This is the center of mass. Angular momentum of the center of mass with respect to the given axis, that is RC P. Position vector of the center of mass with respect to this point or the axis is RCP, LC plus RCP cross linear momentum of the center of mass with respect to the given axis, a reference axis, MVC P. Let RCP be R. This is the point P, the center of mass, this is R. R vector. The velocity of the center of mass with respect to this point, if you stand at this point, you can see that the center of mass is moving perpendicular to this vector because the center of mass moves in a circular path with respect to this pivot, accelerating pivot, or you can say moving pivot whose velocity changes. Therefore, velocity of the center of mass with respect to the pivot, but not velocity of the center of mass. Velocity of the center of mass with respect to ground, because velocity of the center of mass with respect to ground, that is written as velocity of the center of mass, can be given as velocity of the center of mass with respect to the pivot plus velocity of the pivot. Velocity of the center of mass with respect to the pivot is perpendicular to this position vector of the center of mass with respect to the pivot, and this is the radius of the circular track of the center of mass with respect to the pivot. Since velocity of the center of mass with respect to the pivot is equal to r into omega according to the kinematics of rotation, we have RCP cross MBCP is equal to RCP into MBCP. The angle between these two vectors is 90 degree sin 90 degree. And the direction, this is VCP, this is RCP, RCP cross VCP, that is outward or anticlockwise or in positive. RCP is R, VCP is R omega, sin 90 is 1, that is R square into omega, whose direction k cap. Therefore, this factor can be written as R square into omega. This factor can be written as R square into omega, m is multiplied. Therefore, this m r square into omega k cap. The moment of inertia of the rigid body about the centroidal axis, as we know, this is IC into omega k cap plus mr square omega k cap. Omega into k cap vector can be written as omega vector. You take it common, we are getting IC plus mr square, and IC plus mr square is equal to IP according to parallel axis theorem, which states that IP is equal to IC plus mr square. Or we can write angular momentum of the rigid body about this point, L is equal to IP into omega. Well, the angular acceleration we can get only when we can get angular velocity. When you take the derivative of angular velocity, we will get angular acceleration. When you take the derivative of angular momentum, you may get the torque. So, if you take the derivative of both sides, to write dl by dt is equal to the time derivative of IP into omega. Since IP is a constant quantity, for this arrangement, take it out of the derivative. That will give us IP into d omega by dt. d omega by dt is alpha. Angular acceleration of the rigid body is equal to rate of change of angular velocity of the rigid body. Well, we can write rate of change of angular momentum of the rigid body about with respect to this reference point, which is moving with some velocity. is equal to IP into alpha. When you use the equation, the rate of change of angular momentum about any point is equal to the net torque impressed upon the rigid body or experienced by the rigid body about that point. If you apply that logic, you will get, when you write rate of change of angular momentum is equal to torque experienced by the rigid body about the some reference point. When you use this logic, dl upon dt, the rate of change of angular momentum of the rigid body about this pivot can be written as the torque experienced by the rigid body about that pivot. Instead of L, you can write LP about the pivot. Then we can write tau p by substituting dlp by dt as tau p. In this equation, we can write tau p is equal to IP into alpha. Here, tau p is the net torque experienced by the rigid body about or with respect to or relative to the axis passing through the pivot. Here there is a subtle point, net torque. We will talk about this matter now. So we are getting tau p equal to IP into alpha. Here tau p is the net torque experienced by the rigid body about the pivot. What is that net torque? What is the meaning of the net torque? Let me explain. Suppose this point is moving with some acceleration, because the context is Newton's second law of rotation for an accelerating frame. This is the pivot. You are sitting here. Therefore, this is the reference frame. And this reference frame is accelerating. Therefore, I put accelerating frame. When this pivot is fixed, you apply the same equation. When the pivot is moving, you can apply same equation. When the pivot is moving with uniform velocity or changing velocity, same equation we can apply. But there is a change here. There is some point in this equation. Let us discuss this. When the pivot accelerates, the center of mass is, say, on the center of mass, a pseudo force acts. When the reference frame accelerates, you are every time while you solve in physics, observer is a must. The equations of dynamics and kinematics are written by the observer or with respect to the reference frame. So, the reference frame must be mentioned before starting of the solution of any problem in physics. The reference frame is moving or it is stationary. Even though it is moving with a constant velocity or uniform velocity, or the velocity is changing, that will affect the solution. When the reference frame velocity is constant, suppose it moves with the velocity v at this instant. Velocity direction and acceleration direction need not be same, because acceleration of this point, the pivot, is given as rate of change of velocity of the pivot. Let us assume that the pivot moves with an acceleration AP. That's equal to rate of change of velocity of the pivot with respect to ground. When a reference frame moves with an acceleration, suppose a0, you are means the observer is always fixed to the reference frame. The reference frame is an accelerating reference frame. So when you are viewing an object, say a hanging mango, this mango is stationary with respect to ground, with respect to the ground person, ground observer or ground reference frame. With respect to the reference frame 1, acceleration of the mango is 0. But with reference to or respect to this accelerating reference frame, the acceleration of the mango is minus a0. With respect to this person, this reference frame, the mango seems to accelerate in this direction with same magnitude. But with respect to ground, the mango is not at all accelerating. Therefore, this observer or the reference frame may require the presence of an additional force which will generate this acceleration. You are fixed to this reference frame and you are observing that this mango is accelerating towards you, because you are accelerating with respect to the ground in this direction. Mango is fixed with respect to ground. Therefore, with respect to you, the mango is accelerating towards you with an acceleration of same magnitude. When your acceleration or reference frame acceleration is a0 vector, with respect to the mango, with respect to you, the mango's acceleration will be equal to minus a0 vector. When the mango is accelerating towards you, that means you are observing that the mango is accelerating towards you. That is the acceleration of the mango with respect to you, relative acceleration. Therefore, you have to give a logic that somebody is pushing the mango which is causing this acceleration. That somebody is a force, because a force only a force can produce the acceleration. And this force is not arising due to any interaction of the object's external object with this object. This is arising because of the relative motion or relative acceleration. Therefore, this force is called fictitious force or pseudo force. Pseudo force. then you can conclude that with respect to an accelerating frame, in addition to all the real forces acting on the object, for instance, in this case, tension and gravity, they are the real forces because they arise because of the interaction. Tension arises due to the interaction of the string with the mango, and the gravitational force arises due to the interaction of the earth with the mango. But this force is arising not due to the interaction, due to the relative motion or relative acceleration between these objects. Therefore, in addition to the real forces, these are tension and gravity, we have to impose the pseudo force. The pseudo force is equal to mass of the object into its acceleration with respect to u, that is minus a naught vector, or minus m into a naught vector. So, pseudo force acting on the object is equal to mass of the object and acceleration of the reference frame and negative of that. So, pseudo force is equal to negative of mass of the object into a negative of the product of mass of the object and acceleration of the object, no, acceleration of the reference frame. That is very interesting. Pseudo force is equal to negative of the product of mass of the object and acceleration of the reference frame. When you are solving the problems with respect to any accelerating frame, you have to impose the pseudo force in addition to all the real forces. So, when you are weighing or when you are fixed with the pivot is accelerating, you have to impose a pseudo force which is directed in opposite direction of the acceleration of the reference frame, which is equal to AP. Therefore, pseudo force will be equal to minus into the mass of the object into the acceleration of this reference frame or the pivot. In addition to the pseudo force, we have gravity force, we have the reaction forces, Rx and Ry, and other forces acting from outside on the object at different points. Therefore, the torque experienced by the object about this pivot is divided into two parts: the torque due to real forces and the torque due to fictitious or pseudo forces. So, in addition to the torque due to the external real forces such as gravitational force, field force, and the reaction force or the contact forces, you need to consider the pseudo force, torque of the pseudo force. And torque of the pseudo force can be given as position vector of the center of mass with respect to the pivot, that is assumed as R. Therefore, the pseudo torque, we can call it pseudo torque, is equal to torque due to the pseudo force, that is minus m AP R cross position vector of the point of application of the pseudo force with respect to the pivot, that is R, cross the pseudo force, that is minus M, or you can just write minus R cross MAP. So you have to add it here. The real torque, that means the torque due to the external real forces, plus the pseudo torque, that is minus R vector cross MAP vector, or you can just write real torque minus R cross MAP, that is the net torque. After calculating the net torque, you can use this net torque as torque, net torque about this point P. You can write tau P. The tau P is the net torque. The net torque is the torque due to real force, real forces, real external forces. Internal torque will be 0 for about any point. So we don't consider the internal forces. The real torque, or the torque due to the real external forces, plus torque due to the pseudo force. So this is the meaning of the net torque for the, or experienced by, or acting on the rigid body when you are writing the torque equation sitting or with respect to the pivot or sitting on the pivot. This is an accelerating frame. When the pivot moves with constant velocity, if the pivot or the reference frame or axis of rotation moves with constant velocity, velocity of this pivot is constant. So you can say that its acceleration will be equal to 0. The pseudo force will vanish, the pseudo torque will vanish. Then we can just write, the torque about the pivot is equal to the real torque. The pseudo torque will be 0, but when the point of pivot or the pivotal point or the axis of rotation accelerates, then the pseudo torque will come into play. The pseudo force will act at the center of mass, and you have to take the torque of the pseudo force about this pivot and add it with the torque due to all external forces acting on the rigid body about this pivot, and equate it to the term in the right hand side, which is equal to the product of moment of inertia of the rigid body about this pivot and the angular acceleration of the rigid body. That is the idea. However, I can get the same expression by using different technique. Let us take an example. Let us assume a rod which is free to move on a smooth horizontal plane. If we pull one end of the rod, there are two ends, 1 and 2, pull either this end or that end with a constant acceleration is equal to AI cap. Find the angular acceleration of the rod. mass is m, length is l. Find the acceleration of center of mass. So this is a clear-cut case of accelerating frame. This is the point P which accelerates. You sit on this point. This is the accelerating reference frame. This is the center of mass. On the center of mass, we need to apply a pseudo force in opposite direction of the acceleration of the reference point. The pseudo force is ma, magnitude is ma, and direction I have shown, which is negative or opposite to the acceleration of this pivot or end point. It's not exactly pivot, this is the end point. It is constrained to move with a uniform acceleration along x direction. And this pseudo force is applying a torque. There is no other force to apply the torque about this point. Therefore, the net torque is the torque due to the pseudo force. The real forces, you put it on the horizontal plane. The real forces are gravity and normal reaction. They cannot produce a torque about this point because they are equal and opposite. So the net torque will be equal to the pseudo torque. The pseudo torque is equal to L by 2 into F pseudo. Which direction? The pseudo force will turn this rod in clockwise direction with some angular acceleration alpha. So pseudo torque is equal to L by 2 into pseudo force in minus k cap direction. Pseudo force is equal to mass of the object into acceleration of the reference point in inward direction. We know that the net torque applied about this point is equal to the moment of inertia of the rod about this point into alpha. Substitute the net torque here to get the alpha. The net torque is equal to L by 2 ma kf is equal to the moment of inertia about this point we have calculated, which is equal to ml square by 3 multiplied with the angular acceleration. And this gives us the angular acceleration of the rod is equal to 3 by 2. L will be getting cancelled to get L right hand side, and A will be in numerator and L will be in denominator, and direction minus kf. Answer. The clockwise sense or inward sense. How to find the acceleration of the center of mass? Acceleration of the center of mass with respect to ground is equal to acceleration of the center of mass with respect to the point P plus acceleration of this point P. The center of mass acceleration with respect to this point, if the omega initial is 0, it will be in this direction. That is L by 2 into alpha acceleration of the center of mass with respect to this point will be equal to L by 2 into alpha, as per the theory of kinematics of rotation. In which direction? Minus I cap direction. Axis of this point is given as A I cap. Therefore, we are getting A minus L by 2 alpha I cap. And you substitute the value of alpha here. The magnitude A minus L by 2 into the magnitude of alpha is this much, where this is the magnitude 3A by 2L. And direction, L getting cancelled. So this is A minus 3 by 4 into A, that is A by 4 I cap. Answer. This point accelerates in this direction with respect to ground. However, acceleration of the center of mass with respect to the point P is in left hand direction, L by 2 into alpha I cap minus L by 2 alpha will be equal to 3 by 2 A by L I cap getting cancelled, minus 3 by 4 A I cap. Acceleration of the center of mass with respect to the pivot is this much. Acceleration of the center of mass with respect to ground, that is equal to A by 4 I cap. So which acceleration he is asking? We have to see. If nothing is mentioned, only simply he asks acceleration of the center of mass, we have to assume that it is with respect to ground. Or in the next bit, you can find acceleration of center of mass with respect to the pivot. So this will be the answer. You should make a clear-cut difference between these two accelerations. One with respect to this accelerating point, and another with respect to the fixed point with the ground.